Generative media has hit a hard limitation. No matter how photorealistic an AI-generated video is, the output remains entirely passive. Once rendering is complete, the file is a static, unmoving sequence of frames you only watch. A new experimental prototype from Google Labs, known as Project Genie, circumvents this bottleneck. It shifts generative AI away from passive media consumption and introduces an active, playable process called text-to-world spatial synthesis. To understand how this works, you have to discard how traditional video games operate. There are no pre-rendered 3D models here, and no physics engines explicitly coded by developers to dictate gravity or collision. Instead, the system hallucinates the physical mechanics and the spatial environment frame by frame, directly in response to the real-time inputs of the user. Hard-coded spatial boundaries are being replaced by action-conditioned probabilistic generation. The software doesn't load a room, it invents the room the exact second you try to step into it. To manage the compute load, the current iteration of the software operates on a strictly locked 60-second interactive generation cycle. The user interface is standard. You dictate navigation within this hallucinated space using basic WASD keystrokes to move and the spacebar to jump. This creates a dynamic of infinite expansion. There is no predefined edge to the map because the path ahead continuously generates in real time, built entirely off the directional micro-decisions you make in the present moment. Once that 60-second timer expires, you have a few operational choices. You can download the footage, adjust your text parameters, or execute the same prompt again to yield an entirely unique set of physics and topological outcomes. That 1-minute restriction is a deliberate architectural constraint. Synthesizing responsive, interactive frames requires immense GPU computation, and this limit ensures the server infrastructure remains stable. Before you enter the loop, you are given a 30-second initialization window. This is the only time you have to define the foundational parameters of the simulation. The model accepts multiple input vectors. You can type out a descriptive text string, or you can upload a custom image to establish the specific aesthetic baseline the simulation must follow. You can also construct your simulation around real-world topological data by pulling spatial coordinates directly from Google Maps Street View. The system can ingest the layout of a busy intersection in Mumbai and rapidly convert those geometric realities into a fully stylized, mechanically playable environment. If another user builds an environment that intrigues you, a community remix function allows you to extract their base initialization prompts and iterate directly on their design. By condensing the world-building process into a 30-second translation of human intent, this interface democratizes spatial creation, accomplishing in moments what traditionally requires months of manual 3D modeling. Executing that translation requires a highly specific tri-model stack. The first layer is Gemini, which functions as the intent translation protocol. However, raw text inputs are structurally ambiguous. A short description of a sci-fi city lacks the necessary mechanical instructions to dictate lighting physics, collision rules, or atmospheric density. Gemini parses raw text into a comprehensive web of parameters, categorizing the intent into specific environmental rules, physics variables, and aesthetic constraints. These parameters are then compressed and passed down to the next compute layer. By converting imprecise human imagination into a rigid matrix of actionable mathematical instructions, Gemini acts as the critical bridge in the architecture. Those instructions are received by Genie 3, the core spatial foundation model responsible for the actual generation. This introduces the core central technical problem, determining how an AI maps out physical properties like gravity or object collision without a human developer writing the code for those rules. Google trained Genie 3 on massive datasets of unannotated gameplay. By processing countless sequences, the network mapped momentum and trajectory. Now, registering a user's jump command, it references its history of upward trajectories, probabilistically rendering the exact matching frame. Genie 3 does not simulate physics mathematically. It relies on highly accurate probabilistic prediction to fake those spatial reactions with near-perfect fidelity. Generating unique frames probabilistically is incredibly taxing. If the rendering lags even slightly behind the user's physical keystroke, the computational latency destroys the illusion of interactivity. To ensure the system actually operates in real time, Google deployed a specialized internal optimization protocol called Nano Banana Pro. Its sole function is to drastically compress the inference time between the initial user input and the moment Genie 3 outputs the synthesized frame. Executing this low-latency pipeline requires a tremendous amount of specialized hardware, restricting current operation to Google's premium AI ultra-tier server-side infrastructure. Without that sub-second optimization, Project Genie would be a high-quality rendering engine, but it would fail completely as a responsive, playable environment. As of mid-2026, this technology is in a highly experimental phase. Access is currently age-gated and geo-locked strictly to the United States. Because every frame is hallucinated on the fly, the real-time graphical fidelity cannot yet match the polished, pre-rendered realism of engines like Unreal Engine 5. Probabilistic physics also generates spatial anomalies. The engine will occasionally make a poor prediction, resulting in bizarre structural deformations or objects phasing through solid barriers. Furthermore, the massive operational cost of hallucinating a real-time universe keeps the prototype contained within a heavily restricted, non-credit-consuming sandbox instance. But these constraints provide a critical baseline. Despite the geographic limits and the occasional physics error, this prototype represents the lowest operational fidelity this architecture will ever have. While it functions as a consumer gaming prototype today, the true strategic value of procedural text-to-world generation lies in enterprise utility. Safe deployment of embodied robotic AI requires extensive testing. These systems must practice navigating millions of highly varied, chaotic environments to ensure reliable performance. Project Genie effectively functions as an infinite parameter generator. It can instantly output endless, risk-free topological variations for robotic agents to traverse. Human engineers cannot manually code enough physical edge cases to prepare an agent for the unpredictability of the real world. A hallucinating world model easily generates the required chaos. Digital spatial environments will soon be procedurally constructed on demand, adapting instantaneously to the specific training parameters required by a machine learning model or the specific aesthetic desired by a human user. Project Genie provides the proof of concept. AI models now comprehend our spatial reality well enough to dynamically replicate it. The architecture of digital space is no longer coded, it is hallucinated. Generative